Everyone, good afternoon. Am I audible?
Yes, ma'am. We're just adjusting the volumes.
Yes. Okay. Okay.
Good afternoon, Mr. Ashwath. Welcome, Dr. Ashwath.
Good afternoon, Dr. Pillai. Thank you.
Ma'am, some more participants will keep on joining, so I think we will not waste the time of people who have joined already. Hence, we'll
Yes.
start.
Yes.
Over to Ms. Nivedita.
Okay. Okay. Thank you, sir. So let me just start sharing. Anyway, I will be covering some of the related topics that I shared in the last class. So I guess it's visible. So today, primarily, we are going to cover. Okay, so first of all, what we actually have learned in the last class or the first class of this series is that why do we need one? What are the areas where there are certain pitfalls with the classical computing or the way we think classically that needs to be thought again for an alternative method of computing. That was a ground or that kind of a base that we have created. We have seen a bit of like real world problems like protein folding, like traffic flow optimization, logistics, like use cases like supply chain, route optimization. So these are the certain areas, and also the quantum simulation where we actually need to simulate quantumly. If we want to simulate a particle which is not under the scope of the macroscopic level or world, then we need to go to the quantum level or the that kind of a nanoscopic level in order to simulate that particular system. So these are the certain use cases where we have seen that because of a lot of issues like the irreversibility challenge that we have with the classical system, with the time taken, which is due to the combinatorial explosion, the space complexity, because of we have to simulate, we have to actually encode a large number of possibilities into the search space, which increases the space complexity, and also our inability to simulate a quantum space like efficiently. So because of all these 4 or 5 challenges, we have seen that there is a literally a ground where we need to think in a different way. So the way classical physics used to work, that will not be able to work further. So that was the ground that why we need quantum. Then also we have seen that, okay, so there are 2 possible ways of computing. The first one is a DNA computing and the second one is a quantum computing. And why 2 things? What is the similarity between these 2 methods of computing? We have seen that it is a non-determinism. That is our ability to process systems or process a particular logic with possibilities that can exist simultaneously. So it is our ability to process multiple possibilities simultaneously, that is at the same time. And if we are able to encode it through some computing methods, it is basically a non-deterministic model of computation. And we have seen that both the DNA computing, which is our normal brain, the way it works, the DNA that we have with the nitrogenous bases, it's perfectly random. And it's also non-deterministic. That is, we do not know at a particular point that what kind of a nitrogenous base combination we are going to have in the next time unit. Okay, so if we have a adenine and thymine, say, combination, which is A and T with a double bond of nitrogen, we do not know just after that time instance, say at time T, we have A with T combination, then we do not know that at time T plus 1 or T plus 2, what will be the exact combination. That has no correlation with the earlier things. So that is, they're perfectly uncertain, random, and non-deterministic as well. So this is the case for a DNA computing. And also we have seen, because a quantum particle, it has an inherent nature. We will see through the theories of that. But basically we have discussed it, that it has a property where it can behave both like a particle as well as like a wave. Now, whenever you are thinking it as a wave, then wave means it's not a discrete thing, it's a continuous form. That is, all possibilities you can import through a wave format. Someone has raised a hand. Please post your just question. Okay, post your question meanwhile.
Yeah, actually,
Ah,
there is some issue with the audio. It is not from Madam side or from the WebEx side. You can check, and otherwise, because YouTube is working fine. Okay, so please, you can parallelly follow on YouTube. Meanwhile, you also try to check what are the setting issues. Right? We are looking at. I mean, from here there is no issue. That's what I feel. Right, and there are many who are there. Ma'am, you have not changed the slide, right? As of now, it is QT
no,
0.
no, no, no. Yeah, absolutely.
Yeah, yeah. So the slide is not yet started. When the slide, ma'am, you can just move the slide once or twice, maybe go ahead
Yeah.
and then come back. Yeah, so slides are working. So please check voice at the same time, right? And we are looking at these questions, so which are coming in the chat. So please don't disturb, ma'am. Right? We will try to respond to the chat. Right? Thank you. Yeah, ma'am. Please continue.
Yes, yes. So I would request if possible, just try to rejoin. Just disconnect this thing and just try to rejoin. It generally gets resolved in those events. Okay. Yes. Yeah. So what we were discussing it, just like a DNA computing, we also have discussed that quantum is inherently also non-deterministic. Don't worry, I have not done anything with the slides and all. I will let you know once I start like playing with the slides, the slide number 1 and 2. You will follow the context and the slide. Don't worry about it. So for quantum, we have seen that basically it has a property to behave like a waveform as well as a particle form. And whenever it behaves like a waveform, it's a continuous thing rather than discrete possibility. So wave means basically it is a wave, at least you can think it of. If it is a wave, then you can input multiple possibilities into the waveform simultaneously, where probabilistically each of the possibilities can occur, which we refer to superposition. And quantum computing favors this kind of a certain kind of a like powers, which we call the like Avengers kind of thing, which adds power to quantum. So we discussed in a very brief way in the last 5 minutes of our discussion in the last class that what were those 5 properties. So today we will start with those 5 properties and we'll check that what was the theory behind those properties and how we can start manipulating those properties in order to get our desired results, through which we will create a base so that we can enter into quantum computing. Now, what is the difference between quantum physics and quantum computing, or quantum mechanics and quantum computing? Is quantum physics is the way it behaves quantumly. It's the behavior of a particle in the quantum world, certain particles, right? For example, say photons. Photonics also, if you know that electronics is the behavior of electrons, photonics is the behavior of photons. Likewise, quantum physics also is the behavior of the quantum particles in the quantum world in a very easy language. Now, what is quantum computing is, now we have a challenge as a computer scientist or as a researcher for quantum computing. We have a challenge, that is we have a certain, if we are provided with a certain particles which work following the phenomena of quantum physics, are we able to do a certain kind of a logic into them and make them work in the way we want to in order to solve a particular problem? See, ultimately, quantum computing means something you have to go through the computing ways, right? So computing means there has to be some algorithm, there has to be certain kind of an like rules, how we can build it. There has to be certain kind of a manipulation, some results we'll be going to see. So a certain fine tuning with the states possible, all those things you are going to see. So it's completely two different field. And what bridges these two fields is basically a certain set of rules and that is algebra, say for example, and the encoding thing, how you can encode your particular given problem statement, which is in a very like an abstract form, into the physical particles which are there in the quantum world, which follows the principles of quantum mechanics, quantum physics. That is your case. That is, you have to apply as a researcher, you have to apply your computing logic into the quantum physics particles or theorems or whatever it is. In this way, these two fields differ, right? So now we are into that to understand that what are the quantum physics, what motivates us, and how we can think of just putting a particular logic into the those kind of like principles of quantum physics. So yes, just in a nutshell, I will be discussing it. First, what we discussed in 1 or 2 minutes, then I will be telling in a detailed way that what do you actually mean or what are the powers actually added through the principles. Okay, so it's a recap of 1 minute for each of the principles, followed by, I just changed the slide. Right now. Yeah. Okay. Followed by what you can actually do with those things, right? So a more of a practical viewpoints will be shared here, right? So the first property was superposition. It is the power of being in multiple states. So what was superposition? We discussed it's a property that a quantum bit can be thought of to be in multiple states or be having the multiple probabilities simultaneously at the same point of time. That is the meaning. In a very easy language, if you have only one quantum bit, say for example, it can be either a 0 or 1 or both. That is a red you can see or the blue you can see or combination of red and blue you can see, right? Now, whenever I'm talking about a combination of red and blue, I do not necessarily mean that you have to have like watched a certain kind of a 50% of red and 50% of blue. You actually can see just like the full moon, if you see those pictures, right? That how the different after a fortnight how it changes. So it changes very gradually. So it's you can see maybe 30% of 0, then 70% of 1, then 31% of 0, so like 69% of 1. Likewise, we'll see through a transition. But it has a probability or it has a possibility or it has a power to input all those possibilities together, right? So that is the power of like superposition. And whenever it is like perfectly 50% 0 and perfectly 50% 1, we call it a uniformly superposed state, quantum state. And whenever it is, say for example, somewhere not 50-50%, we call it a non-uniformly superposed. Both has a significance. What kind of a significance? Say for example, if you have a 50% of 0 and a 50% of 1 for a particular quantum state with only one quantum bit. What is the mathematical representation of a quantum bit? We do not know right now. We don't have to even know. Just think logically. If we have a quantum unit or a bit which has a 50% of 0 and 50% of 1, and if I try to measure it, what I can see? I can either see a 0 or I can see a 1. It is not predefined. It depends again on the hardware, or it is perfectly random. Conditions applied that we have a setup of a 50% exactly 0 and 50% exactly 1. But say, for example, through your logical sense, just try to analyze it in this way. If you have a 70% of 0 and 30% of 1. Now, if you want to identify that what is going to be your output, if you just tamper the quantum state or just try to get the output, or you just kind of hitting the ball at a random time, what you can see is basically it will of course depend on the how much biased your quantum state is towards a 0 or a 1. If it is 70% of 0 and 30% of 1, you're going to get a 0. If it is vice versa, you're going to get a 1. So that is the power of superposition. But again, the same analogy that I have given in the last class, say for example, your hand is a quantum system. You have 5 such units, which is 5 quantum bits or 5 qubits, 1, 2, 3, 4, 5, which are 5 fingers of your hand. Now, each finger can represent either on and off. Say, for example, my finger down is off, my finger up is on condition. In those particular scenario, you can actually encode how many possibilities altogether with only 5 quantum units. What is the number of possibilities that you can encode? You can actually encode 2 to the power of 5 number of possibilities. Now, if in this line anyone has any doubt, let me know. I'll be like more than happy to explain this line. What I have told is, if you have 5 fingers, then you are actually able to encode 2 to the power 5, that is 32 number of possibilities. Are we all agreeing with it? It is a fundamental essence of superposition. This property is the primary kind of a backbone that gives power to quantum computing. In contrast, if we want to analyze it classically, if you have only say 5 classical bits or classical registers, say for example, right? You have a 5 bit register, then how many information you can store in that? It will be only one, right? Because at a time you can only store at it single qubit of a sequential or parallel with respect to time factor. I'll tell you. I'll tell you. See, sequentially, it is not the way. It is the way you can encode it. So it's all possibilities together. How you will be able to get the output, if that is your question, again, that depends on the individual biasness of all those 5 qubits. So for example, my third finger is little biased to being on top. It don't bend. Then I might get 1 for the third finger. Likewise, it depends on the individual biases associated with each of the fingers or each of the qubits. But it is not the same, or it is not very generic. If it is 100% unbiased, if you do not have any knowledge on how you have built it on, then you cannot predict that what order you are going to get the output. It can be a very random order. Now, that is another challenge that we have to think of whenever we will be thinking of the quantum algorithm. If we want to get a desired output in a particular order, it is our responsibility to fine tune your algorithm in that way so that you can get your desired order also, while you will be getting the random outputs. If you want to have a definite order, you need to work on the logic part. If you do not want to work on the logic part, naturally, it will happen that it can occur in any sequence. Does not matter. 0, 1, 0, 0, 1 has an equiprobable kind of chance with, say, 0, 0, 0, 0, 0 or 1, 1, 1, 1, 1 or 0, 1, 1, 1, 0. All these possibilities are equiprobable. That is the thing. Now, just what I was telling, if you have a classical register of 5, say, bit, how many information you can input with that? Only one. It can be either, say, focus on either. It can be either 0, 0, 0, 0, 0, or it can be 0, 0, 0, 0, 1, or it can be 0, 0, something like that. So ultimately, at any point of time, you can only get one value, which is a 5-bit value. Say, for example, this is 0, 1, 0, 0, 1. But you do not have the chance to hold multiple possibilities together. But if it is a quantum system, then your each finger or each qubit is able to store 0 or 1. So it is 0 multiplied by 0 or 1, multiplied by 0 or 1, multiplied by 0 or 1, multiplied by 0 or 1. 5 times multiplication. So if we do it, it will be getting a 0 or 1 product times, how many times? 5. So 0 or 1 is a 2 possibility. So 2 to the power 5 is 32. I hope this is clear. So each quantum we can actually input 32 possibilities with only 5 qubits, which is we call the superposition. Absolutely, Kiran. 1 of 32 in classical, it can be any one, but in quantum, it is basically say the value of the bit. Yeah, we call here the value of the qubit. But in quantum, it is basically over 32 possibilities. Now there is a challenge. There is a challenge, and it's better to tell it right now because otherwise you might have a wrong notion of it. Don't worry about the presentation. I'm still on superposition. I will let you know once I will just move on. Okay. So I'm just discussing the theory. So just please focus on the theoretical part rather than what is the slide contain, what it is showing. I hope you're understanding. Just focus on the understanding part.
I request the participants kindly, please, we will have to restrict the chat, right? If you are listening to the lecture, you will have no doubt. I'm really little worried because I'm seeing in the group also, many people are writing so many questions and doubts not related to quantum. Now, when the lecture is going on, please focus on the lecture. If you are not able to log into WebEx or something, please go to YouTube and watch it. Both the links are shared. So please focus on the lecture, right? The material will come. The material was shared yesterday. The material YouTube link was shared yesterday. You can watch the YouTube. You can watch the thing. So I'm really surprised what you are wanting to introduce, right? We have shared the video link also. Video is also available. Yesterday's video and yesterday's slide immediately we shared, right? So if there is any issue, please contact, because I am speaking on behalf of MNIT Jaipur links. But if there is any issue, please let us know from other academies also. If some material has not reached or if the video has not reached, we will let you know. Please check your emails, because email and also through the WhatsApp group, both ways we have sent these details. So please check your email, right? And regarding WebEx registration, the registration ID is unique to everybody. Nobody can use somebody else's registration ID. And please do not share the ID. The ID is not going to, the ID number is not going to help you log in, because the WebEx will recognize your email with a registration which you have registered, which you have got on your registered email. We have sent a PDF explaining it. Please open the PDF and read it and follow the instructions. And what I am trying to do now is, after the lecture ends at 4 p.m., we will continue in this link. We will give you a separate Google link, on which Google link, one of you, these issues will be addressed one by one. So all those who have a problem with logging in, please wait. At 4 o'clock, we'll address all these issues, right? And please join the Google link at 4 o'clock. We will send after the lecture is over. Please join the Google link and we will address those issues also. Please do not disturb the class. Do not ask questions not related to the content, right? Yeah, voice issue we will check. And if voice is a problem, please listen to the voice on YouTube. There is absolutely no problem. Please try to coordinate, right? Thank you.
Okay. Yeah. Yes, sir. Yes. So I've seen a certain kind of questions that is, if we get so many possibilities, then how we can actually understand that what is the correct output. It is just that it is not only get the correct output. If you remember, it's about encoding all possibilities together. So you can think it of a bit. I will put some minutes on it so that your doubts, because this is very, very fundamental, so that it gets clear, then only we'll move forward. So it is basically your ability to encode multiple instances of your problem simultaneously into the same, like all those possibilities will be explored simultaneously. In order to facilitate that, you can make it in the superposed way. So, for example, your one superposed state will represent one possible encoding, let's say 0, 0, 0, 0, 0. Your one possible another state will represent something else. So another encoding itself you will represent through 0, 1, 0, 0, 1. Likewise, all the 32 possibilities you can encode. That is the thing, right? So that is the kind of an essence that we're talking about. So there is the question of a correct output or not. So what output you're going to get, you have to put your logic in that way. And all so okay. I don't know. Maybe the way it's okay. Sure. Yes. Okay, now it's okay. Thank you. Thank you so much. Thank you so much. Yes. So I hope it is now audible. I hope it is now audible.
Yes, ma'am. Now you are audible.
Okay. So one doubt I had, that is, out of the 32 possibilities, if I am only able to get all the possibilities together, then what is the, that was your question. Now the answer to this is, it is your power to encode all the possibilities together. It is not the power or the kind of you are asking what you are asking is, it is very random. We are getting all the 32 outputs together. Then what is the correct output? It is not that one. It is not for what we are aiming for quantum. For quantum, what we are aiming for is the combinatorial explosion. Just think of that particular scenario. Now we want to encode multiple possibilities together. For example, it's a traveling salesman problem. What if we say I have only four or say three, very easy one is three. I have only three nodes. Then what if I'm able to simultaneously encode in 3 qubits? Okay, all the possibilities like 1, 2, 3, 1, 3, 2. Simultaneously, now all these things will be explored. It will not be sequential, like 1, 2, 3, then it will be 1, 3, 2, then it will be 2, 1, 3, or
मैडम का प्रॉब्लम है फिर इशू.
simultaneously. So that is the power. Now all the 6 possibilities will be explored simultaneously. You will be calculating the optimal path, and whatever you will be finding as the least, say cost, you will tell that, okay, this is my best solution. So that is the kind of way we try to encode it. But remember, here we do not really use a multiple quantum processing units. Just like for a parallel computing, if you want to encode it, then it will be it will be basically, you have to put different processing units in order to process the different kind of possibilities. But in quantum, it is a one quantum system which has a 5 qubit, where each of the qubits is basically representing the kind of possibilities. So that is the way we are thinking to encode. And out of the 32 for a 5 qubit system, you can get any one of the 32 possibilities if you do not do any auto tuning or fine tuning into your system. You are very much like equiprobable to get any of the output. This is a challenge. You might ask, then that is not the way we want the solution to be. Absolutely. So in that case, what you need to do, you need to form your quantum algorithm. It has to have some certain kind of an algorithm or logic. That logic is the computing thing. It has the ability to explore simultaneously. That's the part of quantum physics. Now you're understanding what is the difference. You are able to encode 32 possibilities together. How you are getting this benefit? Through quantum physics. Now, where the quantum computing comes into picture, that is, I now have the possibility to encode 32. So what I should be encoding? Should I be encoding the nodes? Should I be encoding the edges? Should I be encoding the paths itself? And how I can manipulate those encodings, and how it can go through several kind of a time evolution. That is, with course of time, the quantum states will, I have to evolve, I have to transform, I have to reform in a way I get the optimal output whenever I want to have certain ones. For what I want to have, our logic should be able to work in accordance to those things. So that is the thing. That is the thing that we have to take care of. I hope it is now clear. So let me just now go to entanglement. So, okay, the second one was entanglement. Yes. So for entanglement also, it is like a special kind of a quantum leap. So I actually told the cases of Durva, where it was a story of like two Salman Khan playing in that movie, where whatever you are doing with the one say character, that the similar kind of an effect you can see with the other. Now again, it has a certain benefits. It has a certain benefits, and it has a certain kind of a disadvantage as well. Okay. So what is the benefit? The benefit is, now you have to think it out with the use cases. What are the possible use cases that you can do with the entanglement is, and say for example, you want to devise a quantum kind of a quantum setup where you want to check that whether two systems are in a perfect correlation with each other or not. where you need this kind of scenario. I just had told a bit of it. You can see the similar kind of a scenario for quantum communication as well as for quantum cryptography, where it is your kind of a like requirement to check whether there was any tampering done with the system or not. If, say for example, as or they two are communicating with each other, so they will try to have an entangled pair, okay, both of them, so that if they want to have a common key, for example, just take it up in this way, common key or a shared key to set it up, they can use the benefits of entanglement theory. So part of the key, at least they can generate through entanglement. So whenever there is any kind of a checking whether the key shared or the part of the key shared used in order to generate some encryption key, okay, whether that is in the same phase or in the same say correlation or not. Correlation generally is expressed in terms of amplitude. It can be either on and off, or it can that is 0 or a 1, or it can also be expressed as a phase. What is the phase of that one? Whether how much it is deviated from the standard phase. So that phase deviation is also used for the correlation. Please let me know if you have any question. Entanglement is basically there are certain quantum gates for each of the use cases, like for superposition, for entanglement, for interference. So all those things we will be discussing whenever we will be actually discussing the quantum gates. All of these concepts will again come back. Okay, but how can we understand the result corresponds which way? Okay, now how you can understand it, what is the result is how you were interpreting your result to be. So as well, you have to say that, okay, that this particular combination should mean this particular thing. Say, for example, how many places you have your even numbers. In those places, you want to have one. Okay. In those, I'm coming to your question. So in those places, I want to have a one. So once I have all these kind of possibilities where from the position of the bit itself, I can predict that, okay, these positions have even number in that into that array. So in that way, so what you are getting in the output is what you have encoded in. That exactly is going to get in the output. It is just the possibility to explore simultaneously or possibility to encode simultaneously. That is the feature. That is the feature. So in terms of a lesser number of queries that you have to make from the output, is what benefit you can opt for. It is not in terms of uh, absolutely, Saloni, exactly the same thing. So it is not really the way uh, it is not really the way that is, it is very abstract one. It is encode a quantum system will encode it in its own way through some quantum bits. You will be getting some result that you will be unable to predict. Not that. It is your algorithm that you will decide. You as a researcher or a like specialist will decide that what one to encode. Again, for with respect to a graph, you can either encode a nodes, or you can encode edges, or you can encode path. So with simple case, for just for a graph, you can actually input three possible things. Now again, what you want to encode, whether it's want to encode the in degree or out degree particular thing, whether a certain kind of an adjacency you want to encode. So your way of encoding is what we going to get as an output. Okay. Yes. Now, next question is to Saloni that how entanglement is different from position. It's absolutely different. Position is my five fingers, my ability to say I'm a multitasker. I can do multiple things simultaneously, being the same processing unit. I do not have a clone's mind, but I can do that. But entanglement is, say, for example, I'm Qubit and my best friend resides somewhere else. Okay, and we both are somewhere related to each other. Whenever I'm sad, she's feeling sad. Whenever I'm happy, she's also feeling happy. Or we are best enemies. Whenever I'm feeling sad, she's feeling happy, and vice versa. So entanglement is relation to states, like two states of universe. It is not, and superposition is only with respect to one particular qubit. Now, it's like or one particular say, quantum state. If it is, say, for example, a 5 qubit system, then it is a superposition of 32 states. If I have a 3 qubit system, then it is a superposition of any possible states. So it is all superposition is always with respect to one particular quantum register and how many qubits it has. But entanglement is always related between two systems, which are totally different, and how they are related to each other. In that way, we want to be. Now, we can also say, for example, I have a 5 qubit system where I am telling that qubit number 1, 3 will always be in entanglement. That is, they are not independent. The output qubit 3 is always somewhere dependent to qubit number 2 and vice versa. So that is a interrelationship or kind of correlation between the qubits. Whenever we are talking of entanglement, but superposition is just the superposed possibility. I can be in multiple states. It is my possibility. It is my possibility. Absolutely entangled qubits because can also follow superposition. If you want, it can obviously follow. But even after that, whenever you will be measuring it or when you will be encoding, you have to keep it in mind that there are certain places where you cannot see the of independent activity qubits. It somewhere be correlated or differential. Got it? Got it? Much kind of an abstract thing. So, what is parallel universe in terms of mathematically? I do not know, but it is just the way it's kind of you can relate it with the teleportation. Though quantum teleportation is another concept. We'll about it whenever the communication will start. Quantum communication. It's just that it is kind of a telepathy or a teleportation. As of now, we can think it of in this way. It's between two best friends or two best enemies. That is the best example or the say analogy that you can keep it in mind. And also no cloning and entanglement. They are again absolutely different. Let me just go to no cloning. I hope entanglement is at least a bit clear. Don't worry, in every classes we will see a different kind of definitions and intuitions behind these kind of theorems. So at the end of everything, you will have that kind of a philosophy behind all these things. Neither it's fully computing, nor it's fully philosophical. So it's a blend of all those things. In order to understand it, nothing is happening here classically. So the way you measure a system, the way you think you can encode a system, it is absolutely different for quantum. You are not going to see the same flavor. Okay, I hope it's clear. Okay. Now interference, let me just come. I will again just say once the no cloning theorem. So the copying limitation. No cloning theorem says that you have a particular quantum state. What it is, I do not. I'm a Xerox machine. Okay. You have come to me and you have not disclosed what was your initial setup criteria or parameters the way you have set up a quantum state. Right? You're asking me that, okay, hello, Xerox machine, can you clone my state exactly the way it was during my initial setup? My answer will be no, I cannot. That is a no clone theorem. I cannot clone an arbitrary, focus on the arbitrary word. I cannot clone an arbitrary or any arbitrary quantum state. It is not possible. Okay. Why? Because whenever it is so quantumly evolving that once a quantum state is set up, if it is in a very ideal condition, say for example, it has a certain kind of a restriction on its setup, then it can be, say, cloned or something, but that is very specific. But Xerox machine does not really need to be a very specific Xerox machine, right? It has to be a very generic algorithm. That is, if any paper comes with any kind of writing or anything on that paper, I should be able to clone its content. Is another thing. Similar to that, For quantum cloning, these particular things not possible for an arbitrary quantum state. And where it is very useful, it also is a very kind of a deep interpretation in quantum communication and cryptography, where I believe that if an intruder wants to get a particular quantum information which you are sending in form of a quantum state. Remember, you are sending in form of a quantum state, within double quotes, quantum state, not a classical state. Classical state information can be flown, but you are sending something through a quantum channel, a quantum state of information. Now, it is not possible for an intruder to intercept it, just get that information that okay, you are okay, so you are sending these things. I've got it. Okay, now let me be in masked way. So I will again try to clone your system and I'll put the original one, not the distorted one, into the packet and let it go through the quantum channel. This particular thing is not possible. Now are you understanding what you are actually like bringing into picture? What are the real applications or the security aspect you are bringing to the picture? You are actually bringing the like exclusion, or you are removing the possibilities of man in the middle attack or meat in the middle attack. It is not possible. What is man in the middle attack? Someone in between of A and B. Say Alice and Bob. Say Eve. He or she will sit basically into the channel, hearing whatever information, and try to get that, and behave or pretend as if she was the intended recipient, or she has not done anything. He's a very a very good person, which is not the case, real case, but because she has intercepted. So these kind of a middle letter that we have in classical system, say for example the key exchange, during the key exchange with the Diffie-Hellman key exchange algorithms, all those things. If you are well aware of the classical cryptography, so for those kind of there are a lot of, not only KFC, there are a lot of scenarios in classical cryptography where you face this kind of problem of managing the metadata. It is not possible if you're sending some information input and encoding it into a quantum state and then sending it, because a quantum state, once you just try to poke that thing, definitely it will be only one outcome. Again, remember the superposition theorem, out of the 13 possibility it can be exactly one. So only one we get it. And from the output, it can be trace back what was your initial setup. You cannot really clone the initial superposed state. That is not possible. Right? Maybe it was 65% 0 and 35% 1, or say 39% 0 and some percent of 1, 61% or something. You cannot clone the exact superposed step. So if you cannot do that, that packet will go in the exactly same way, in a distorted way, to the receiver, intended receiver. Say Bob, Alice and Bob are communicating, Alice is sending the data, Bob is receiving the data, so Bob will be getting the same thing. Now Bob, what he will do is, once he will get a packet, he will understand that okay, no, it has a certain kind of a distorted feature into it. Okay, it is not the same thing that I should be receiving. It was not upon our initial agreement that I had with Alice. So I should be discarding the message. So that particular message or that particular part, the key will be not used for sending any sensitive information. Now it's a input. So right now I can ensure that okay, through flow cloning theorem, I can actually imply a kind of an intruder free, or the detection of intruder 100% possibility we have for a quantum states. That is the business impacts that this no cloning theorem is bringing into picture. And all these things like superposition, entanglement, no cloning, all of them the fundamental or fundamental properties of quantum physics, which we are using in computing. Slowly, for everything, just try and analyze that how the physics and computing they are getting, like there is a perfect blend of these physics. Okay. And decoherence is the enemy of quantum computation. Everything comes with a certain kind of limitation. Decoherence is once you have a quantum state, you have checked it at 2 p.m., say for example, it has a particular setup. You have checked it, okay, that it has this much of amplitude, checked, phase checked, okay, properties checked, all the angles checked, theta, phi, whatever is, there are a lot many phase angles. We will be discussing it. All those things check, check, check. Okay, this is the set of zero with this probability check. You actually went somewhere to the market. You came back at 2:15. Now you're checking. You'll be getting a different read. You come back at 2:30. Maybe, say for example, you have not tampered anything at 2:50. Just check the reading. You'll be getting something. 2:30, you check it's getting another set of reading. So what does it mean? With course of time, it decoheres. This is the time decoherence. Second kind of decoherency, say for example, you have something, right? Very easy example. Say two friends are there who are targeting for say GATE or NET computer science or any subject. They went for to the exam center. Once one student has a certain kind of he studied something, he has that thing in mind. Another student also had went with his parents with all the tika and all with a certain kind of again preparation in mind. Now, whenever we have actually seen this thing in real world, and I can tell you, when we will see those students, once they meet just like before say 30 minutes of their examination, they will try to share what they know. It is their inherent nature. They will definitely share. They will be like not be there with the parents anymore because they have seen their old friend. They will just try to meet with them and then they will discuss. Okay, so यहाँ से इस in 2018 IRC Bangalore asked this question which I actually missed. So do you know what is the output? Then whatever is your belief and then he will tell you his belief. So somewhere it will be mixed up. Right? This is also another incoherence that it is called a coupling decoherence. It is a cross coupling decoherence basically. You are communicating with your neighbors, and because of that interaction, what information you had earlier that went lost or that actually had now become distorted. So the coupling also causes a kind of a decoherence. Second one. So first one was a time decoherence. Second one was a coupling decoherence. What was the third one? Third one is, say for example, now uh, you have read something and don't have the book. Okay. Now you're traveling to the exam center, say by through some public transport, and for 3 hours you are just coming. And meanwhile, you're meeting with different people. There is a signal thing. There is an issue. There was a kind of a maybe traffic police actually interrupted you, asking you certain questions. So this kind of scenario is whenever your neighbors, like through whom you are interacting while you are under process, while you are in process of certain computation, those neighbors, while interacting, you might not get your intended neighbors. You might actually maybe in an argument with someone else. Say 7 rupees was the fees while you were taking, say, while you charging me 10 rupees for auto, for example. Say. So all these non-intended kind of neighbors in quantum, they also cause certain kind of a discomfort. It's a real world. It happens quantumly, so it has a very similar analogy to the way we think. So it is the same thing. Your neighbors also will cause a disturbance. So what you should be doing? You have to be in a society or you have to be in a very nearby to your exam location so that you get a very minimum amount of distortion. We all, I guess, somewhere in our career we have followed this thing that okay, let's just book a hotel or something which is very nearby so that we can face a minimum distortion. All form of distortion is basically related to decoherence. As of now, just have these kind of three things: one caused by the neighbor, one caused due to the courses of time, logarithmic decrement kind of thing, and one is due to the coupling decoherence. Have you all got it? I hope now at least you have a basic fundamental understanding behind the logic. Theory is theory, but you have to understand the logic. Okay. So anything that is caused by the environment that can affect you, it has a great effect and a similar effect in quantum system. So now And researcher, what you can do, you have to think it so that your greatest enemy, and that is the decoherence, that gets minimum kind of an effect in real time while you are computing something. So it should not be able to manipulate your system anyway. So you have to be manipulative with the algorithm itself so that your decoherence doesn't come into the picture. Right. So one more thing was there, which was this thing, interference. I guess interference we do not have a much of an issue. This it's a similar kind of a pond where multiple waves, say for example, a water wave is there, where you throw another stone, so it will create another wave. Now, if you just follow those two waves, somewhere you will see that two waves are cancelling off each other, somewhere they are maybe constructing a bigger wave. So these kind of things are called interference. Which interference is a very generic property, right? So for quantum also, if it forms a bigger wave, it is called a constructive interference. And if it forms a smaller wave, then it is called destructive interference. Before mathematical, I have to tell what will it mean is, for example, where constructive interference is those scenarios where my possibilities are being added up. Possibilities are being added up. Say, for example, if it is Sunday, I have to go for a movie, then maybe I will be having my lunch, then I will call my friend, then I will be going for a movie. Remember all the phrases that I am choosing, okay? So I'll be having my lunch, I will be calling my friend, then I will go for a movie. So I have clauses in and B. So how much is the probability? For example, so that all the clauses are equiprobable. It is equally important for me to have completing my lunch, and as well, it's my task to complete my like calling my friend. So 50-50% is. Then I will go for a movie on Sunday. What if I tell you that okay, there is another possibility? Let me just add it up. Let me just add it up. That I will be completing my lunch. I will be calling my friend, and I take permission from my parents. Implies I will be going for a movie. Now it is a constructive interference. Why? Because my possibilities are being added up. But what is happening here? If you remember very carefully, see the earlier probabilities that I have with me for mine having completing my lunch and go for a movie was 50%. And calling my friend and go for a movie was 50%. But whenever I am adding a possibility, that I have to also take consent from my friends. Then what I'm aiming for? I am aiming for a 33.33% possibility for each of the three cases. Clear? Are you getting it? Are you getting it? Let me know. Instead of unpredictable, also see here that here the probabilities are getting diminished. So whenever you have two possibilities, it could be 50-50%. But whenever it is like you are adding up one more possibility, then you are adding another possibility. That is, say for example, you have to also take consent from your in-laws. For examples. Now it's cases are 20, 25, 25%, 25%, 25%, 25%. Initially it's 50-50, then it's 33.33. Now it's 25%. Likewise, in constructive interference, probabilities are being diminished for each of the possibilities. Definitely your possibility is going to increase. Because we all know probability. Even if it's superposition, it can never exceed 1. The maximum value of probability can only be less than or equals to 1. Okay. For figures and diagrams, you have to wait for like those kind of series, and these are very generic examples that I'm taking. Definitely, don't worry, those things will also come because in quantum, abhi tak they couldn't make more principles into it. So these are the same these kind of things, just in different shades of light. You will be watching. It's better to have that intuition with you. Now, after this computing intuition, once I go to the theory, quantum physics today. in the later half, you will understand it that okay, it's like just nothing. It's nothing. It's basically your understanding will be absolute. Okay. And similarly, now think of a destructive interference where you are cancelling out the possibility. I don't understand that if you have a like four possibilities, you can have that you do take consent from your in-laws. So your individual possibilities will actually increase. So it will be 33.53%. It will be then 50%. Likewise, gradually increase. Because again, your summed up probability of instinct. It's a very basic probability, nothing related to quantum. Probability of a particular thing event can never exceed one. It can be maximum one. That is okay. And there is a theory of perfectly like exhaustive event and all. Considering even that thing, it can be one, but it can never exceed one. I guess all of you just actually agree with the probability. Probability of nothing can exceed one. So with that note, with that note, so this is a kind of why these principles make quantum revolutionary. The summary of quantum advantages, all these things are advantage, superposition, then a summary, then followed by entanglement, followed by interference, then no cloning theorem and decoherence. Okay. Now, 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 no, nanocomputing, I am not well aware of nanocomputing, first of all. Because I do not know the engineering of it. So, what are the particles and all? Whether it's exactly quantum or it's a blend of classical quantum, I do not know. I have to check it, or you can also check it differently. But I guess there are a fixed kind of particular kind of hardware specifications are there in order to be it with quantum. I guess you can also check it and let me know the next class. Okay. So next is why does classical physics fail at small scale? So basically, it's a transition from Newtonian physics to the quantum physics through a several kind of discoveries. But in our curriculum, we have those things so that we had kind of like history of how these things evolve. These are very theoretical. I hope through very easy examples we'll be getting it. So classical physics, which is the Newton's laws and all, explains everyday macroscopic phenomena. But you know that in atomic scale, it collapses. I guess right now you know that what are the cases where it collapses. We start with that thing in our class, that it will collapse. Then ultraviolet catastrophe and black body radiation. The classical theory predicts that the black body radiation should emit infinite energy at high frequencies. Okay. And through the equation where it is energy of one quantum in joules, joule is the like SI unit of energy. H is the Planck's constant, which is has this particular value, constant value. It's an approximate value. It will be, I guess, 6.634 or something. Just an approximate value I've given here. And nu is the radiation frequency in hertz. So it states that energy is not continuous, but it is quantized. So these are the evolution of the thought processes that led to these discoveries, that led to the researchers or scientists to move into quantum gradually. Okay, initially it was thought that energy is not continuous, but it's like quantized, and so absorbed or emitted in discrete packets, right? And this is the thing. What was the key insight? That light behaves like a like particles, like individual energy quanta or photons, not just waves. So basically, in short, light has a particle feature into it. That was the discovery. And photoelectric effect did also the same thing, light as particles. Like classical prediction was increasing the light intensity should eject more electrons, regardless of the frequency. And Einstein in 1905 discovered that electrons are only ejected if the light's frequency exceeds a particular threshold, no matter what is the intensity. So, what is your conclusion? Light is not just a wave. It has that particular kind of quantization factor. Quantization means it has to be a certain kind of particle field. That's why we call it quantization. Even in the pulse width modulation and all, if you remember from analog to digital, ultimately the waves they are actually quantized through sampling, quantization, and coding. So ultimately, we try to predict it, how it can behave in particle way. So it is a conclusion that light behaves in the particle format or the photon format, carrying energy equal to each other. Right? Part two, there was another discovery called quantum scattering. It's saying that light has a momentum, a certain kind of a momentum. What do you mean by that? That classical physics said waves have no momentum, but experience showed that transferring energy to electrons like tiny billiard balls. So it says that light behaves like a particle. It has kind of a mass and velocity both, contradicting classical wave only explanations. It is a particle, it has to have certain kind of a mass and it also has a certain kind of velocity. We'll see all these four things separately as well. And the fourth one is the double slit experiment, which says that so basically that is it has also a like a wave-like behavior that is governed by the Schrodinger equation that is, you will be seeing certain kind of an interference. So it's a double slit experience. Electrons being particles should pass through one slit or the other forming two bands. That is, they will not be on the plane, on the say the projecting plane. It will not be exactly made at a certain point, it will not converge, but it will also create a band kind of thing. We have all seen it. If we just focus a torch light on a dark room, we have seen it. There is a certain kind of a wave kind of a thing or band kind of things also forming. So from all these things, what we have understood is what we have understood through all the experiments, we have understood that okay, that means light is something which can behave as a wave as well as a particle. So the black body radiation and Planck hypothesis that actually says that okay, so energy is quantized. The same theory. Energy is quantized. That it is in form of discrete energy. Let's have seen like E equals to h. So for these things, say for example, we understand us through a story. Say imagine we have a metal rod heated in a furnace. First it will glow red, then it will have some other color. At extremely high temperature, it will shine as another color. But why this kind of color change happens with temperature? When they try to explain it through the quantum physics, they actually believe that a heated object should emit radiation continuously at all frequencies. But when they measure it, that the energy emitted at different wavelengths, that is lambda, okay, which is nothing but in meters in SI, they check that the results do not match really the classical way they have predicted things at all. It has a particular out on say particular values. So a formula called the Rayleigh-Jeans law predicted that as the wavelength decreased, the emitted energy should keep increasing indefinitely. This meant ultraviolet light or UV light should have some infinite energy, which was completely unrealistic. So the incorrect prediction was called the ultraviolet catastrophe, which is not there. Now, Planck came with a hypothesis, which is the groundbreaking hypothesis in this thing. So he came with a radical idea that instead of an energy being emitted in a smooth, continuous like matter, which says, what if we say that energy is released in a very tiny discrete packets, which is called a quantum or quanta. The plural of quantum is quanta. So what if we can say that light is nothing but some packets of energy, which is called quantum. The higher the frequency of light, the larger the energy of each quantum. So the idea meant that at very high frequencies, energy emission was limited, avoiding the UV catastrophe. Though Planck introduced this concept as a mere mathematical trick, but it laid the foundation of quantum mechanics. And if you also see the quantum physics, quantum, the word quantum comes from the word quanta, which means a discrete packets of energy. That is the fundamental definition of quantum physics. So you can actually observe it. So in short, what do you mean? In short, you mean that light is nothing but some discrete energy packets. It is in form of some particles which are energized forms of, say, just packets form of uh, quantized energy, right? So this was the first step toward understanding that nature isn't continuous at the smallest scale. It is rather quantized. Okay. Second one was, first one was energy is quantized. Remember this point. Second point was a photoelectric effect on Einstein's quantum light. So it is another kind of a like support to the earlier fact that light itself is made up of particles or photons. Have you ever seen an automatic sliding door that open when you say something, put something before them? They often use certain kind of motion sensor based on the photoelectric effect and all these things. So when light shone on a metal surface, it ejected tiny particles, right? But what is the weird part? The weird part is the brighter light did not always eject electrons. It does not necessarily mean if you increase it continuously, it will eject electrons in that way. Only light of a certain minimum color or frequency that worked, even if it was very dim. So increasing the brightness just increase the number of electrons, but doesn't increase their inherent energy. So classical physics again had no explanation for this because we know that everything, whenever we are expanding, it will be more like of ejection in form of electrons, and definitely this kind of ejection of electrons happens whenever there is a increase in the energy, or it's a kind of a more kind of a heat dissipation and all those things. So classical physics had no explanation. At wave theory of light, any bright light enough light should eventually knock off electrons, but it didn't happen. Even for a dim light also, it was able to produce something. That again means that light is made up of certain kind of a particles that has quantized factor into it. So it's basically the photons. And this behavior is called photonics, the behavior of photons, how it behaves, even if it has a dim light or it has a brighter light. So what are the factors this thing is dependent on, all those things. So Einstein's radical idea was light is made of particles. After all these observations, he proposed that light isn't just a wave, it rather is also in a form of a tiny particles called photons, where each photon carries a fixed amount of energy, called a quantum of energy. If this energy is enough to overcome the bond holding electrons in the middle, then an electron gets ejected. If the photon's energy is too low, so low that it cannot eject an electron, then no, definitely no electron will be emitted, no matter how bright the light is. So it depends on the energy. Briggs, in fact, was this proof that light behaves as both a wave and a particle, opening the door to the wave particle duality of quantum mechanics. But it is not yet very much confirmed. But it at least opens the door that okay, it has a certain kind of a duality thing. Light cannot be exactly like a wave. It has a certain kind of particle fusion as well. It opens the door. Okay, and remember quantum, now again go back to the quantum computing stuff where we started. We started with this thing that light can behave in both the wave form and the particle form, and that we call as a non-deterministic power of a quantum computing. Now again, just a bit of like analogy I want to draw here with the superposition of those theorems. Superposition is when light is in wave form. Now I hope you are understanding it. So state 1 having probability, say for example 0.25, state 2 having probability 0.25, state 3 having probability of 0.5, and state 4 having the probability of 0.25. That is, we have 4 quantum states, each have the same probability of 1 by 4, right? When all these things exist together, it will be in a wave form. But whenever I will try to get one value out of the 32, the person who has asked this thing, the same thing, whenever I want to get one particular output, it will be in the quantized form. So only in that case, I can see certain visible output. Whenever it is in a wave form, I cannot get the output. I can only get the output when I have exactly one state or a fixed definite number of states. Again, a definite number of states, not exactly equals to the number of the superposed states that I had initially. So for simplicity, as of now, understand that out of the 32 state, it collapses to exactly one state whenever I am trying to get the output. And that particular one state is known as, actually happens when we do a certain sort of quantum measurement. Okay, and when we do the measurement, it loses the quantum property. So right now, out of the four states, it will be exactly one state. Say state 2 is the popped of 1. It is out. State 2, out of 1, 2, 3, 4. State 2 is out. What should be the probability of state 2? It will be 100% now. Again, why? Because of the interference thing. Are you understanding how these things are related? Initially, it was 0.25. Now I am deleting, or whenever I am measuring it, whenever from the waveform I want to get certain output in the particle form, I am actually cancelling out a certain possibilities. So whenever I'm trying to measure a quantum system, some of the possibilities will always automatically get cancelled out, and you will be able to get only one output as your like final output. Okay, that state can be anything again. That state can be anything. It is absolutely random. Now, if you ask me a question, if it is absolutely random, then what's the point of doing it? I will not never be able to get the result out. You might be having this question. The answer is, in order to get your desired output, you have to form the logic. But what I am able to give you as a quantum computer, I'll be able to process all your 32 possibilities or your 4 possibilities or whatever you give me simultaneously. I'll be holding all the results simultaneously. I'm a quantum computer. Whenever you ask me a query in classical way, and in the last step, okay, now just show me the output. What is your step? What you are currently holding? I will be giving you exactly one value out of those 32 possibilities. If you do not know how to tune me, I can give you any output in any way I want to out of the 32 possibilities. It will be anything. That depends on my inherent biasness, my hardware biasness to a particular state. That can be any sort of biasness. That can be qubit biasness. That can be my like quantum gates, quantum circuits. Any level I can have any biasness. Depending on that, I will be able to give you the output. It is perfectly random. If you do not tune me, it's perfectly random. Whenever you're tuning me, whenever I'm in a waveform with all the 32 possibilities, I've explored all the 32 possibilities, done all the computation, say addition function you have given to me. I have performed the addition function on all the 32 possibilities. I hold the value for all the 32 possibilities, but I'm unknown to you. Now, if you ask me a question, what is your output? I can give you any one output. Right? If you want, okay, then show me the superposed form, I cannot state. But state you cannot.
Hello, uh, ma'am, your audio is lost, I think. Are you able to hear me? Yeah. Okay, let me talk to ma'am. Yeah.
Because I can like hear all of you. Am I audible now?
Now you are audible, ma'am.
Okay. Yes,
Please go.
I could hear all of you and I could see the all the comments. Yes.
Right. Okay, ma'am. Now you are okay.
Okay. So where I actually left, can anyone guide me on that? So till what part we actually was able to hear? Right.
Yeah, one
Okay.
of the possibilities, that was what you were discussing.
Yes. So I hope, just let me know if you have got till this point or not. What I have asked you, if I am a quantum computer, I'm a quantum computer. So if you give me the query to process, say, 32 additions with all the 32 possibilities, that is, I have to perform an add function, say, for example, add A comma B, kind of that, with all the on all the possible combinations, then I'll be doing it all together because of my ability to do the calculations in a superposed way with all the 32 like combinations, but I'll be holding the value. Now, if you ask me that what is the output, as a quantum computer, I have a full provision to give you any of one of the outputs I want to. And what output will come, that is very, very much hardware specific, that is biased, that is not controllable. Maybe the ones who have done that, even the ones who have actually built it from very scratch, they also might not having the detailed understanding because it is happening in the quantum level. Why 32 possibilities? Just because we like started with the five fingers story where like 2 to the power 5, 32 possibilities. I'm just giving an effect that it might be more than 32. No, if I have 5 qubits, it cannot be more than 32. How it can be more than 32? Say for one finger can be 0, 1, second one can be 0 or 1. For first finger, what is the possibility? Say 0 and 1. How many possibilities have with the first finger? 2. For second finger, 2. Third, 2. Fourth, 2. Fifth, 2. It can be either on, off, or it can be up or down, anything. Or I say head or a tail. Binary logic is binary, right? So it can be either on or off, simply. So 2 to the power 5 is what we can do or what we can have maximum. So it's a 2 to the power 5, that is a 32 possibility. From that story, actually, I picked the 32 like states. Now, once you have those 32 possibilities, if you do not know how you want me to work on those 32 possibilities and which of you exactly want from me, what I'm telling is, as a quantum computer, I will be in waveform. Remember the photoelectric effect, what we were discussing? So I will be in waveform. I'll be doing calculations in a probabilistic way with all the possibilities, no matter whether it's like to the power 3 or to the power 4 or to the power 5. It can be anything. That depends on what is my hardware setup, how many qubits I have. But I'll be doing everything. Now, if you ask me what will be the output, that can be anything, that can be random, or that can be very much like specific to my inherent biasness through a particular input, or say qubit, that input can be qubit, that can be some circuit, that can be I have a faulty quantum gate, or my gate error, decoherence, a lot of such stuff. How you can actually help in getting the desired output that you want to. Yes, it will be very much unpredictable as well as random. The order also is random. If you ask me, okay, what is the answer? Quantum computer, I will tell you, okay, my answer is 01001. Again, if you ask another query, that okay, now again tell me what is the answer. I might not tell you 01001. I can also tell you some other value. It will be random. In a perfectly random setup, it will be absolutely random. Now, the thing is that again, this is now physics. How to make it computing flexible? You have to give me the logic that once you have computed all the 32 possibilities, till this point, you are in a waveform. Now, I want you to behave in a particle form with the desired output. That desired output getting logic, you have to give it to me as an algorithm research. That is the essence of quantum algorithm, that you have to give it to me. I will not be having any access to. So quantum hardware is able to do till this part. Now it is the algorithm or the researcher who will be devising the algorithm. They have to specify that what you want. Accordingly, you have to devise your logic. I hope you are getting it. But once you devise that logic, you ask me the question that okay, you say for example, you devised it in such a way that out of the 32 possibilities, which work on say adding up to random number additions. That two random number can be through some logic it is coming, say for example. But your task is, say you devised a logic that out of that case, you have to give me what was the minimum like summation value. In which case, in which particular qubit setup. So for example, for 01110, I get the minimum output, which was 45. Likewise, you computed all the addition. Okay. And wherever you are getting the minimum value, which is 45, we are telling, okay, so your correct answer is 01110. Here you are getting your desired output. Whenever you are telling this, now see, this is a fixed output. This is the particle behavior of light. So this is the photoelectric effect we're talking about. Initially, it was only on the waves thing, where it was thought of to behave like a superposition. Now you can understand that, okay, it behaves in a particle fashion as well. Okay. I hope right now it's clear. I just need one or two comments, or if you have any questions, or to have some water. So if anyone want to ask any question. What? Okay. Any question you have? Just post the question. Mm, Just a 1 minute break I'm taking for having water. I will be using whiteboard. I will be definitely using whiteboard whenever I will be entering into a mode of mathematical stuff, because honestly, all those things like putting them into PPT is very tedious job. So I'll be using the whiteboards for doing it. Even in the earlier FDP also, like I used it for the quantum algorithms and the logic things. So definitely I will be doing.
Yeah, a lot of mathematics will be taught, so don't worry. And the slides with which ma'am has written, she will save it and give it to us. So no problem. You can refer to the whole equations that she writes. You can because we'll be using whiteboard shortly, right? These are the initial lecture. This is basically to revise quantum physics, right? So I have attended the previous time ma'am has taught. So lot of actually the foundations are built. So that, but don't worry. See, the point is we should not be afraid of quantum computing. So please look at that. Yeah, ma'am, you can also suggest some textbook source of this information, because this is coming from multiple sources actually. You will not find it in one book, but yeah, at least definitely we'll try to look at some source where ma'am will suggest. Yeah.
Individually, some of the like fuel sources where you will be getting a very crisp information, so that it's like decodable. You will be understand to decode it. That's the primary objective. I'll be sharing it. But that will take some more time for me to like finalize, but definitely I will share. Yes. And also, while I am preparing it, I'm keeping in mind that we do not have to be an expert in quantum physics. Neither we can be an expert of quantum computing. What we for these initial Q201, what we can definitely be an expert of these, just to understand the bridge between these two things, or how the computing things actually evolved, how it is really difficult, or like not difficult, then different from the classical way of thought process, and how the different physical notions of quantum is related to the computing notions. I guess a lot of us are from like computer science or electronics or electrical, from all the mathematics, all those backgrounds. So it is very important for us to ultimately able to use those theoretical concepts. So if we do not map it, every phenomenon, if we do not map it to the real quantum computing, then it will be of no use. So keeping that in mind, and of course to make you all understand the fundamentals of quantum computing, that was my like primary target while designing the content. I'm just focusing on that. We should always start from something we know to something we want to know. There should be a like arrow, right? Instead of directly jumping into what is a quantum entanglement, it's very difficult. And it almost like I am into this thing, whatever study I have started. And it took so many years for me to understand Grover's algorithm. If any one of you has heard of this thing, so there are like at least 3 to 4 interpretations of Grover's algorithm. But right now in Qubit, right now in other platform, you can just see a particular kind of function, call it with Grover. But that is just implementation levels. But the inclusion level, it is like through several interpretations. It almost took like 2 to 3 years, continuous efforts, so many like trials and errors just to understand it from the paper itself, what it can mean. And then even right now also, maybe I know just 20-30% of Grover. That is what I believe, because actually I have to ask from the Grover himself to understand it. So it's very difficult. Honestly, quantum is very difficult. It's very new, it's very difficult. So we have to be very much patient. Okay. Yes. So this is the second one. Third one is the momentum-like behavior of particles, the strange behavior of X-rays. So, which basically says that, say, light waves should not lose energy just by scattering, but yet they did. They lose energy, first energy, during the scattering of light. If we just hit something and then wait for its behavior changes, then we will see that, yes, it differs with respect to the energy distribution. So it comes from the Einstein's idea that light is made up of particles of photons. And when one photon collides with an electron, it loses energy and it changes its direction. Just like two billiard balls collide, or just like any object, any two objects that collide with each other. Okay. And this showed that the photons don't just carry energy, but they also have a momentum despite having no mass. Okay. And the impact was, this was a proof that light behaves as a particle, further cementing the way particle really. So all these three things that we have studied, the black body radiation theory, then the like Planck's, then Einstein's theory, then the Compton scattering theory, all these things actually are to confirm that light has a particle picture. And the last one is the double slit experiment, where there were two slits and light sources of light was passed through the two slits, and at the like say wall you can see an interference pattern, which say that light also behaves like a wave. That was the thing. So this introduces the part of wave particle duality, that the quantum mystery, electrons act like waves as well, and particles can behave as waves. And observation changes reality. The act of measuring alters the outcome, which forms the foundation of quantum mechanics. The act of measuring alters the outcome, okay, which forms the foundation of quantum mechanics. Okay. And can give you any of the outputs. That depends on your way of inputting into the real world, like real settings. Got it? Okay. Now the need for quantum mechanics. Now you know these things. Okay, yes. Now that we have understood that so basically all those four experiments was just to tell you a typical features of light, which is the wave nature as well as the particle nature, right? And it has certain kind of moment. Now the thing is that the quantum state. So, what is quantum state? Instead of this theoretical slide, let me just first tell you in a very easy language what it is. Then we will discuss this theory. Then we will also see that what is different between a classical state and quantum state. Okay. So that is the like so far what agenda we have for today. I guess here only we are ending or we have something. There is a scrolling to the equation and there I guess we are ending. Okay. Think perfect with the time and all. Yes. So from the examples that I have been giving, let us follow the same format. So how it is represented a quantum state, that's a different thing. But what is a quantum state? Quantum state is any state represented in a quantum computer while it is under action. That can be at the very beginning, that is the initial setup, or that can be while the experiment and all those things are in progress, or it can also be at end. But any state with a particular like quantum bits or quantum logic into it, applied on that kind of thing which works in a quantum computer, is basically called a quantum state. What is a classical state? The same thing. Whenever you are just putting the same thing on a classical computer, it's a classical state. And similar things, whenever you are putting on a quantum computer, it's a quantum state. But there is a difference in the way you write it down, right? So from next class, maybe I will be doing a certain next class means from Monday. Actually, I do not have the pen tab here. Let me try if I can manage it. Otherwise, I will just check for other maybe sources. So if I have something, I'll try to have like use those things. Okay. So quantum state is basically how it is represented. It is represented through some bracket notation. Now, all these things will again come. So don't like worry about the mathematics and all. These are like a lot of mathematical things. We will be discussing. But as per the curriculum, because we have to follow the curriculum also, these are the things that are introduced at a very earlier level so that you have a basic idea what is a quantum state or what. Whenever I refer later that okay, this is a quantum state, you are able to understand what do I mean by that. That is primary objective. Okay. So if we it's like a 32 possibilities case, say for example initially you have a coin with you with you, right, and you were just flipping the coin, right? Now remember each and everything, just focus on everything. You have coin with you, right? So it is a quantum system. Your coin is a quantum system of one qubit, right? One quantum bit or one quantum unit you have. Now, whenever you are tossing your quantum coin, what it can be? It can be either a head or a tail. That is your one. Now your one qubit quantum system. Now your one qubit quantum system has quantum steps. First state is head state. Second state is a tail state. Easy. This is for a one qubit. Say for example, you have right a two qubit quantum system, right? A two qubit quantum system. With two qubits, how many combinations you can get? Either you can get a 0, 0, or you can get a 0, 1, you can get a 1, 0, you can get a 1. So that is four possible quantum states that you can encode with two qubits. Easy, no confusion. What are the states? 0, 0, 0, 1, 1, 0, and 1, 1. If you want, you can also make a copy of it, make a note of all these things, but I'm telling you what. If those things are not present in the slide, you're of anytime you're allowed to take notes. If you have three qubit quantum system, for example, that can be, say, what can be the possibilities? It can be 0, 0, 0, or it can be 0, 0, 1, or it can be 0, 1, 0, or 0, 1, 1, or it can, no, not 9, it has actually 8 possible, or 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So it has 8 possibilities, right? So now we say that a three qubit quantum system has 8 possible quantum steps. State is 0, 0, 0. This is one step number 1. 0, 0, 1 is the second step. Just at least for today, understand the terminologies. We will be referring them in tomorrow's speech. Absolutely. Multiple number of qubits. Those many quantum states you can have. And what is the state itself? For a three qubit quantum system, now qubit is 3. There is only one quantum system. It has 3 qubits, 3 number of habits, and it has 8 possible states. So states you have is Q0, which is 0, 0, 0, Q1, which is 0, 0, 1, Q2, which is say 0, 1, 0, Q3, which is 0, 1, 1, till where till it is Q7, which is 1, 1, 1. So from Q0 to Q0 to Q7, you have 8 quantum states. I hope at least you have clear, like I have a clear understanding of what is a quantum system. It is one quantum system only. It is how many qubits? It has 3 qubits. How many states? 8 states. Till this part, it should be very, very clear. Now, if I give you a 10 qubit quantum system, then it's a one quantum system. It has number of qubits is equals to 10. And how many total possible number of states can be there? Just post it on chat. If I have a one quantum system of 10 qubits, then how many quantum states I can have? 2 to the power 10, which is 1024. I hope that is clear. Right? Now, again, come back to the superposition stuff. What is the interpretation of those many quantum states? Those many 1024 quantum states mean that again depends on your encoding. But if you can encode, you can actually encode 10 things to explore simultaneously using only 10 qubit quantum system, which is one quantum computer with only 10 qubit. You are able to encode all 164 possible quantum states. Clear? Till this part is clear. Okay. Just give me 1 minute.
I think ma'am wanted to take a break. Just 1 minute. She'll continue.
Yes, yes, yes. Uh,
Uh, Ma'am, your voice is not coming. एक मिनट मैम वी आर नॉट एबल टू हियर यू Screen is visible, but the slide is not full screen. Yeah, now slide is full screen. Audio, ma'am. Hello. Yeah. Ma'am, you are not audible. Can you speak?
Madam has to unmute. She is not unmuted.
Yeah, yeah. No, she is unmuted on this. Unmuted. She is unmuted. चैट में कुछ लिख रहे हैं क्या? हाँ, नीचे हाँ, ऑडियो ऊपर देखो, ऑडियो पे कुछ लिखा उन्होंने. Let me rejoin her. She's rejoining. Hello, ma'am. We tried to mute and unmute you. Can you try now? No, you are unmute only, but we are not able to hear your voice. And you are able to hear you, right? Hear us.
The microphone को allow किया और इस टाइम जान कर दें permission भी हो रहा है.
नहीं, अभी तो हाँ, Ma'am, when you rejoined, please check your microphone settings once, whether the permissions were given or not to WebEx.
Am I now audible?
Yeah, now you're audible. Yes.
Okay.
Yeah.
So that 1024 settings that I was talking, the 1024 settings I was talking to. So whenever we have like 10 qubit system and the number of system is 1, so that is 1024 number of possibilities, which in turn means all the 1024 encodings is parallelly doable.
Ma'am, the screen is not shared.
Okay. Okay. Oh, sorry, my bad. Just forgot to share it. Mistake. Yes. Yes. So the 1024 states is parallelly, you can encode information accordingly. Now, similarly, now you can understand that only with a 10 qubit system, if you have a noise-free, error-free quantum system that we all are aiming for, maybe by 10, 20 years, we'll be having that as well. So we can actually do all those calculations simultaneously. So the RSA problem, the protein folding problem that we were discussing, those problems will get resolved as and when the quantum computer evolves and it actually refines and it makes it like the decoherence stuff, all this. It works on all the different engineering aspects and the logic itself will be more fine-tuned. And similarly, now if you have say, and this is so exponential. Now, if you have say only kind of a 20 error-free quantum bits you have, a quantum computer or a quantum system. Process. This is a huge advantage that we're going to get. So here where you can actually claim that yes, you can do an exponential speed up if you apply a quantum computer. Exponential speed up in terms of computing multiple possibilities simultaneously. Okay. Now the thing is that how this is represented. Now you've understood that what is a qubit thing, at least the notion wise you have understood it. And it is a one quantum system with a few number of qubits in order to give you in return a few number of quantum states. Now the question is that how you can represent those quantum states. Okay, for the representation, because whenever we'll be doing computing, we have to represent it in some way. So mathematically or logically, they are represented using a Kate notation. So you can now check on the screen, like a one bar, and then this is a Kate psi, and followed by a angular bracket. So this kind of notation is called the Kate notation. There is another complementary notation of this thing, the Kate notation, which is called the bra notation, and together they are known as a bracket notation. So this is the fundamental way to encode or to write any quantum state using a bracket notation. So this is the Kate notation that the one you can see, and when you have a left angular bracket, then the Kate psi, and then a vertical bar, okay, then it is a bra notation. Why here I have only used Kate notation? I'll be definitely discussing about those things in next class, the bracket notation in very, very detailed way. But the thing is that mostly the quantum states are represented using Kate notation, because Kate notation is equivalent to the mathematical column vector format, right? So these notations are represented using a column vector. Because all those things ultimately whenever they will be computing it, these are basically matrix form. So all those things make it easier for us to understand. But also the complement notation, which is a part is a characteristic row vector form. And just to give you a glimpse of how these things evolve, only one thing. Now we will be discussing the quantum states on the bracket notation, universe space, all those stuff in the next class. on Monday, but just to give you a glimpse of how we can represent it from one qubit to qubit, so that you also be able to tell that what will be in the 4 qubit or say 10 qubits. Okay. If our one qubit is there, in 5, whatever you say, like you do the work at scale has, it will be for information 0. We represent it in form of a ket 0. And for information 1, we represent in form of ket 1. Ket means the vertical line, then 0, then angular bracket close. Otherwise, angular bracket is 0. Put in place of 5 or psi, if you put 1, it will be ket 1. You put 0, 0, it will be ket 0, 0. You put 0, 1, it will be ket 0, 1 likewise. So we are going to use this kind of notations from next class onwards. And what is the meaning of these things? So this is the notation. So mathematical form is clearly right. So just remember, whenever I say ket 0, it means a column vector 1, 0. So on top it is 1, on bottom it is 0. That is, a column vector means a 2-row and 1 column form. That is a 2 cross 1 column vector which has a 1, 0. Ket 0 represents this thing. Ket 1 will represent and 1. Just the reverse logic. 0 will be on top, 1 will be the bottom. This is a 1 qubit system, right?
Uh,
If you have a 2 qubit system,
Nivedita ma'am, I think voice is breaking actually. So I think maybe I think it's because of the if you're using headphones, I think the battery is low, I think.
oh, it's okay from my side. Is there any issue?
Now it is okay. Now it is okay. Yeah. Now you can go ahead.
Okay. Okay.
I
Okay.
think you keep the mic close to where you are. I mean, I think because you are moving, maybe that may be the reason. Yeah, sure. Go ahead, ma'am.
Okay. Yes. Yes. Okay. Yes. So, Kate, I guess right now it shouldn't be a problem. Last few minutes.
Now it's better.
Sure.
Now it's better.
Sure. Sure.
So
Yes.
maybe you
Yes.
can start from the ket notation part. Yeah.
Yes. So, Kate 0 basically, I have said that why we have used Kate notation. First of all, I've explained that one because we will be having the column vector format representation because column vector are mostly used for matrix multiplications as an operator. Whenever it operates on some matrix, it will like the multiplication is easier, first of all. And secondly, uh, I say that ket 0 is represented as a 1, 0 column vector, which is a 2 cross 1 column vector. Okay. So where on top it is 1, bottom it is 0. This is the representation of ket 0. And ket 1 is 0 on top and 1 on bottom. Okay. If you have any doubt, just let me give more qubit example to you. Say, for example, I have a 2 qubit system where I have how many states possible? 4 states. How states are represented? Through the ket notation. So that means state 1 will be nothing but 0, 0. I guess state 2 will be 0, 1. State 3 will be 1, 0. And state 4 will be 1, 1. Till this part, I guess there is no kind of, none of you disagree till this point. Now, if I say that 0, 0 ket, you have to represent it in the column vector form. How you will be representing it? You can represent it in a way, better to write. Yes, I will be writing. I will be writing in the next class. I'll be writing them. Don't worry. Or if I do not have access to the pen tab for the next class because it's not right now with me, so maybe I will just try to like follow some other online tools so that I can use or some other format I'll be definitely using or handwritten notes also I can just add with multiple examples. So I'll just be like taking the images. I hope that will be the last policy or the better policy also. So I'll be just writing them down, all the explanations and all. I will put it in as an image. I will put it directly into the slide. I hope that will also be helpful. with each and every detailed explanation, like of examples. I guess that will be very helpful. So, as of now, just remember that one, what we was telling, that we have a 2-qubit system. So we have 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, where 0, 0 means I have a 4, for all these quantum states, 4 states, I'll be having, I can represent it with a 4 cross 1 column vector, right? That is a 4 matrix. Okay, so 0, 0 will be represented as 1, 0, 0, 0. A 4 cross 1 column vector I'm talking about. That means it has a 4 number of rows and only 1 column. Only 1 column. And on top it is 1. Then on bottom it is all 3 zeros. And it is for 0, 0. Okay. Now, if it is 0, 1, it will be 0 on top, then 1, followed by 0, 0. Right? If it is, say, 1, 0, it will be column vector, where it is, just remember, whenever I say like 0, 0, 1, 0, it will be just like a 4 cross 1 column vector. Just try to put values in that way. So for 1, 0, it will be 0, 0, 1, 0. And for 1, 1, it will be 0, 0, 0, 1. Clear? Now, this is individual states, 0, 0, 0, 1, 1, 0, and 1, 1. If I tell you what will be the superposed quantum state, one quantum state which is superposed. Superposition means superposed with all the 4 quantum states, 0, 0, 0, 1, 1, 0, and 1, 1. How you can represent it in the column vector form? Can any one of you tell me? What will that be? In very easy words, it is nothing but, say, 1, 0, 0, 0 plus a column vector 1, 0, 0, 0 plus another column vector 0, 1, 0, 0 plus another column vector 0, 0, 1, 0 plus another column vector 0, 0, 0, 1. So it's a very simple matrix addition, which is nothing but 1, 1, 1, 1. Just one column vector 1, 1, 1, 1. So what do you mean whenever you see a certain kind of these kind of values? It means that it is a superposed quantum state. Now remember here, till this part, till today, we have ended with only the amplitudes, which is also not very, we have just started with the amplitudes. We have to now deal with the probability, because in probability theory, because quantum is fully, why not the Brown notation? Yes, I just told, because whenever we will look into the more of the examples and the matrix multiplication. So all the quantum mathematics is mostly the bulk part is of the linear algebra, very simple fundamental linear algebra and the complex mathematics. So the linear algebra part is basically with a lot of like matrix multiplications in a very nutshell, or the core is that one. And with the row vector notation, whenever we apply it on a particular operator or some operator applied on this particular quantum state, which is represented with a row vector, that operator itself works in a well-suited format with a column vector notation rather than the row vector form. Yes, that is the bra and kit. These are called the dual. Shouldn't be. Is it no audio? Someone has written no audio. Don't know why.
Ma'am, that was earlier, I think. Now you are clear. No problem. Please go ahead.
Okay. So just remember in this part that a superposed state will be represented with 1, 1, 1, 1 in a column vector format, and that is through simple matrix addition. But we have not till date talked about the probabilities or the probability and amplitude, how they are related. So there is definitely a relation, because it anyway has to be normalized, and probabilities can never exceed 1. So initially it was the probability of getting 0, 0 is right now 1. Initially it was only the probability of getting 0, 0 was 1, and all the other 0, 1, 1, 0 and 1, 1 was 0, 0, 0. So it was okay. Similarly for all the remaining 3. But whenever you are telling that it's a superposed one, you are putting all the ones here, definitely it's not 100% right now. So that is where the probabilities will get distributed. And we will check how it gets distributed as and when we increase the number of steps. Okay. So let me just pause here, and exactly from this point, with these bracket notation and the representation of similar things, we will actually start our next class. And next class maybe mostly with the handwritten or maybe note. So instead of writing it, because in real time it might be very difficult also, because if I do not have any pen tab. So there is a lot of literature and that kind of issues. So I'll be just writing it down and do some like as an image I will post it on the slide. And that slide I will be showing and explaining each and everything. Actually. It is that way. Absolutely. Yes.
Yeah, I think, ma'am, you're completed for the day, right? मेरा दिखा दो, unmute.
So,
You share, you don't have already.
Hello, are you able to hear me?
Pillai sir, yes.
Yeah. So please look at the schedule as you look at. So we started yesterday and we inaugurated and we had the lecture by ma'am. So we'll continue these lectures till Saturday, from Monday to Saturday, and after Saturday, that is on the Saturday, that is date March 8th, we will have 4 hours lecture by Nivedita ma'am. Kindly note, right? It will be from 2 to 4 hours. There will be one lecture. There will be slight break of 10 minutes or something, and then another 2-hour lecture by Nivedita ma'am herself on Saturday. So please note this. Instead of having from 2 to 4 on Saturday, we'll have from 2 to 6. And on March 9th, we'll have that will be the end of this content on quantum this thing. So that will be quantum communication. She will start just briefly, and after that we'll have the exam. So that exam will be on the syllabus that has been covered: basics of quantum physics until quantum computation, right? And after that, she will continue from 10th to 12th, another 3 days. She will continue till Thursday, that is right, Monday, Tuesday, Wednesday. Yeah, okay. So that will be a break from 13th, 14th, 15th, 16th. 4 days we'll have a break, that is till Sunday, right? So March 9th is Sunday, and we'll have a break till 13, 14, 15, 16. Okay, I think there is some confusion here. Okay, let me check. And so after that, again, Dr. Ashwath Babu will start taking the lectures from 17th onwards, and we'll go on till March 22nd. So I think there is some confusion here. So let me just check. I think we'll go on till Monday is 10th, right? So 13th and 14th are holidays, right? 13th, 14th, 15th, 16th. Can you respond in the chat? Would you want holidays for 13, 14, 15, 16? Because it is holy holidays. So that's the reason why we have kept 13, 14, 15, 16 as off. 15 anyway, 13, 14 we wanted to break, but 15th also some people may be traveling, and 16th anyway we are not conducting the class. So these 4 lectures have been adjusted on Saturday and Sunday, and also on last Saturday, that is 22nd. So we'll have a lecture on 10th, 11th, 12th, and 11th and 12th. 13, 14, 15, 16 we'll have break for 4 days. And from 17th onwards, we'll start quantum sensing. That will be by Dr. Ashwath Babu. He'll take from Monday to Friday. And after that, on Saturday, it will be IBM team who will be talking about advances in quantum technologies. So that is the schedule. If some of you are here, would like to look at those people who are struggling for that. So we'll try to send another WhatsApp, Google Meet link also. So please join. I'll be sharing on the WhatsApp group. So you can continue, you can look at the demonstration, and then if there is anything else you can look at. The slides for today and the YouTube link will be shared shortly. In another half an hour time, you will get the this thing, recorded class link, that is YouTube link, and also the slides will be shared. So please follow. For those who have problem joining on Canvas or on WebEx, we are going to do a demonstration both on this and both on this and also on or otherwise we'll move to Google Meet.